Hi, everybody. This little thing out of the middle of my screen.
To minimize it.
Yeah. Okay. Hi, everybody. My name's Tyler Gordon. I'm a graduate student in the astrobiology program. My home department is the astronomy department, where I ordinarily work with Eric Agel on transiting exoplanets. But today I'm talking about my research rotation project, which I completed with Baptiste Chernow in Earth and Space Sciences. And I'm talking about water worlds, modeling the structure of exoplanet hydrospheres. Thank you. All right, so I wanted to start off by giving a little bit of background about water worlds. So this is a plot from Dressing et al. 2015, onto which I've overlaid a whole bunch of exoplanets, some of which have been discovered since then. So those are the black points that you see on top of this plot. And the tracks across this plot represent mass and radius values for planets with different compositions. So in the bottom right, you have the composition for a 100% iron core or planet. And then as you move up from there, we go through varying degrees of incorporation of magnesium silicate into the structure, all the way up to a 100% water planet at the top. And what I want you to notice here is that a lot of these black dots sit quite a ways above that 100% silicates line. So that implies that these planets have volatiles incorporated into their structure. Water is one of the most common volatiles, so especially for cooler planets, we expect that those planets should have substantial envelopes of water, or what we would call a hydrosphere. So I want to show a picture now of what a planet with a thick hydrosphere might look like. So this is a schematic from Baptiste's 2022 Nature comment, showing a water world that has a rocky core, or a metallic core, a rocky mantle. I'm going to refer to the whole non-hydrosphere part of this as the core, so the rocky core of the planet. And then over the top of that, we have a hydrosphere that's made up of two components. The first component closest to the interior of the planet is a high pressure ice mantle. And then sitting on top of that, we have a liquid water ocean. So if you're interested in the habitability of a hydrosphere, we have two questions that we want to ask ourselves. So the first one is, does this hydrosphere have liquid water somewhere in its structure? So an environment where life can form and evolve and carry out its functions. And then two, we want to know if that liquid water layer has access to solutes from the rocky interior. And the reason that that's important is that life, of course, doesn't only need water in order to survive. It also needs access to materials that it can use to build itself up and incorporate into its biology. And so those would come from the rocky interior of the planet. And if that rocky interior is completely locked away under a layer of high pressure ice, then the concern is that it doesn't have access to the solutes that it needs. In reality, we expect that these high pressure ice layers might be permeable. So you can see in this picture, we have a couple indications of transfer of materials through the ice mantle. One is convection in the high pressure ice. And then another that we're showing here are plumes of solute rich material that's welling up from the base, from the hydrosphere core interface, where there might be some amount of basal melting going on. And I'll talk more about that later in my presentation. And so now I'm going to outline our approach for investigating the structures of these hydrospheres. So the first thing that we did here was to develop a representation of the thermodynamics of ice 7. So there are existing representations for lower pressure ices up through ice 6. You can see on the right a phase diagram of water with pressure on the x-axis and temperature on the y-axis. So as you go to higher pressures, moving from left to right in that plot, you go through ice 6, and eventually at pressures over 2200 megapascal, you enter this ice 7 regime. So that's the one that we didn't yet have a representation for. So my part in this project, or the first part of this project for me, was to work on developing a representation of the thermodynamics of ice 7 that we could use in order to model planets with much heavier hydrospheres than you could model without incorporating ICE7. The second part of this project was to use that thermodynamic representation to compute structures for hydrospheres for planets with different sizes and compositions of core. And then the third part is to categorize those structures in order to understand where in parameter space habitable environments might occur. So I'm going to dive a little bit into the thermodynamics part of this, and I'm going to try to make it sort of brief because this is the unfun technical part, but it is important because it was a large part of the work that I did on this project. So we represent the thermodynamics of these ices using the Gibbs free energy. The Gibbs free energy is a thermodynamic potential. It's a function of temperature and pressure, and it allows you at any temperature and pressure point to derive other properties of the ice, like the heat capacity, compressibility, density, and others as derivatives of that potential surface with respect to pressure and temperature and combinations of pressure and temperature. The advantage of this kind of formulation is that by relating all those properties back to the same Gibbs energy surface, we ensure self-consistency between all of the different properties of the ice. So in the past, people that have done this kind of work have used completely separate representations of the different thermodynamic properties, so independent parameterizations, which means that you don't guarantee self-consistency between the different properties. So that's an advantage of using this machinery to do this work. We represent that potential surface using local basis functions. So this is essentially a sophisticated spline fit where you've imposed regularization conditions on the spline fit to ensure the continuity and smoothness of the different thermodynamic derivatives. The advantage of this way of representing the surface is that it allows for fast computation of the Gibbs energy and the thermodynamic properties of the ice. You can make that representation consistent across phase boundaries by making sure that the Gibbs energy surfaces line up at, for instance, the boundary between liquid water and ICE7 or between ICE6 and ICE7. This representation has already been computed previously for ices up through ICE6. And so again, my part of this work was to develop a similar representation for ICE7. We based this on fit to the equation of state by French et al. In their 2015 work. So we took their work, translated it into the Gibbs energy space, and then fit this spline to it to get our representation of the Gibbs energy surface. Okay, so now I just want to walk briefly through how we actually compute the structure of this hydrosphere. So what we do here is I want you to imagine that we're integrating upwards from the interface between the base of the hydrosphere and the rocky core. And we take layer by layer, we compute using the representation that we have for the Gibbs energy, the properties that we need of the ice at that location. And then in combination with the surface gravity at that point in the hydrosphere, we can advance the temperature and the pressure upwards to the next level in the hydrosphere. And then recompute the mass and the radius interior to that shell in the hydrosphere and iterate in order to compute a pressure temperature profile all the way up to the surface. In reality, often we're interested in doing this in the opposite direction because we don't necessarily know what the pressure and temperature are at the core mantle interface. So the way that you can do that is by setting as an input the total mass of the hydrosphere and then integrating downwards and iterating that integration a few times until you converge on the mass that you expect in order to get a consistent structure for the hydrosphere. We make one major assumption when we compute a structure in this way, and that is that the hydrosphere is adiabatic. This is a conservative approach to computing the structure in that it gives the smallest possible temperature gradient. So as you move downwards from the surface towards the interior, the temperature is only rising by as much as is necessary. Any non-adiabatic hydrosphere will tend to have a larger temperature gradient, so you'll get warmer faster as you move towards the interior. And that means that hydrosphere will be, if anything, more likely to be able to support liquid water in its interior than the more conservative adiabatic hydrosphere. Another thing that happens if you get a super adiabatic temperature gradient is that tends to kickstart convection, which then suppresses the temperature gradient back towards the adiabatic case. So this is a good approximation. It's one that's been made for Earth's mantle, which is obviously rock and not ice, but the principles are similar, as well as the interiors of icy moons in the solar system. So now I want to start talking a little bit about the actual structures that we computed in this way. So as a first example, I present to you the cold, wet Earth. This is a version of Earth. It has a core that's the same mass as the Earth and a composition that's the same as the Earth, giving it the same density and radius. And then on top of that, we've dumped 2.5% water by mass of the total planet. And so what you end up with is a structure that looks like, on the left, I have a cutaway of this structure. So you have a crust of ice, ice 1H, that's ordinary ice, covering a liquid ocean layer. And then below that, you see the high pressure ice mantle, so ice 6 and then ice 7 just above the rocky core. On the right, I have a track and pressure temperature space superimposed on the phase diagram for ice. So you start out at the surface at the very left of that diagram in the ice 1H regime. And then as you move towards the interior, you increase in pressure and temperature and move diagonally across that plot through liquid water and then into the ice 6 and eventually ice 7 regimes. So now I want to talk about how we categorize these hydrospheres. So I'm showing you a phase space here where we have on the y-axis the total mass of the hydrosphere as a percentage of the total mass of the planet from 0 up to 2.5%. And then on the x-axis, we have temperature from 240 Kelvin to 300 Kelvin. And I'm going to walk through and show you what each of these different regimes in this phase space represent in terms of the structure of the hydrosphere. So over on the very left here at cold temperatures, we have hydrospheres that are ice all the way through. Obviously not super advantageous from standpoint of habitability. In this case, we're at high enough pressure that we have that we go straight from ice 1H to ice 2 and then 5 and then 6. If I moved up to even more massive hydrospheres, then there's going to be more pressure at the bottom of the hydrosphere, and you would start to see ice 7 forming at the very base. In this orange regime, we've increased the temperature a little bit. So now our pressure temperature tracks go through the liquid water part of the phase diagram. And so we move from an ice crust to a liquid water ocean, and then again, a high pressure ice mantle, in this case, ice 6. If we move to lighter hydrospheres so that there's less pressure within the hydrosphere, then we can actually have liquid water in contact with the core. So this is a case that we expect to be pretty advantageous for potential habitability of a system like this. Because you have liquid water directly contacting the rocky core, you can have easy exchange of solutes between the two to get material into the ocean. From there, if we increase in temperature, we end up in this regime that I've shaded with the dark blue, where you have water all the way down from the surface to the interior. So these are warm planets with relatively thin hydrospheres, so you don't have enough pressure building up at the base to form high pressure ices. Moving up from there to thicker hydrospheres where you do have more pressure, we again see the formation of high pressure ice mantle underneath the liquid water layer. And then I've labeled separately, I'm just staying within the same category actually. First, increasing the pressure so that we can see the formation of ice 7 as well as ice 6. So here we have a very thick ice mantle. And then I've labeled separately, so this is another case where we have a liquid water ocean covering an ice mantle, but I wanted to separate out the part where we have an ice mantle that's entirely made up of ice 7. So you're moving here from the liquid water regime in the phase space straight into the ice 7 regime. And the reason that I wanted to separate that out is because there's reason to think, this is work by Hernandez et al. 2022, that the ice 7 mantle may actually be more permeable to solutes than an ice 6 mantle is. So ice 6 is a stiffer ice that permits fewer solutes to move through it into the liquid water layer, whereas ice 7 might allow for more of that transport to happen. I want to show you these same sort of phase space plots for a couple of different planetary cores. So that was all for the Earth core case. Here I have up on the top left a core that's half the mass of the Earth, but has 75% iron by weight. That's the X sub Fe. And so this is a denser core than the Earth is because it incorporates more iron. On the right, we have the same iron content, but a core that's twice the mass of the Earth. And so what's happening there, because you have a larger, denser core, you're decreasing the range and parameter space over which you can have liquid water all the way down to the core, and you're increasing the part of parameter space over which you have high pressure ices forming at the base of the hydrosphere because you have more gravity, and so you're crushing that hydrosphere and creating higher pressures at that interface and building up high pressure ices. If we go to the bottom left, this is the lightest of all our cores. It's half an Earth mass and has only 15% iron by mass, so it's a less dense core than the Earth. And here we see the opposite happening. You've sort of relaxed the hydrosphere. You have less pressure, and so you've increased the range of hydrosphere masses over which you can have water all the way down to the core. And then another intermediate case in the bottom right is the case where we have a core that's twice the mass of the Earth, but is a lighter core. Well, not lighter, it's twice the mass, but a less dense core. This is a plot that's showing something similar. So this is placing all of these simulations on the same set of axes, temperature on the x-axis and water mass ratio on the y-axis. And these are the outlines of the region in which you can have liquid water in contact with the core. So to the left and above these lines for a given simulation, you have ice all the way down, or ice in contact with the core. And then to the right of these lines, you have water at the base of the hydrosphere. And I've colored these actually by the surface gravity at the core hydrosphere interface so that you can see as the surface gravity increases, you're going from darker colors to lighter colors. So top left to bottom right. For very high surface gravities, you've again kind of crushed that hydrosphere so that you have high pressures at the base, and you're creating a mantle of high pressure ices. And then the final thing that I want to note is that if it is the case that ice 7 is more permeable to solutes than ice 6 and other high pressure ices, then you could maybe consider everything. So everything to the right of about 291 Kelvin here, you're going straight from a liquid water ocean layer into a high pressure ice mantle that's entirely ice 7. So you might consider everything kind of to the right of that line to be potentially advantageous for habitability, because you may have more exchange of solutes in that scenario. So I want to give a number of kind of qualifiers to this work as I wrap up here. The first is that the big assumption we've made is that the hydrosphere is adiabatic. I already mentioned this. So any conduction in the hydrosphere would result in a steeper pressure gradient and a warmer interior. Also, from the other end of things, any amount of heat flux up from the core into the hydrosphere would result in melting at the bottom layers of the ice mantle. And that would encourage convective transport of solutes towards the ocean layer, and could also give rise to plumes of molten solute-rich water that may plume up through that ice mantle and provide solutes to the liquid water layer above, to the ocean. The other major qualifier here is that in reality, the atmosphere and the surface and the hydrosphere in this case are coupled to each other. So we've looked at kind of the hydrosphere in isolation. You would imagine that water planet would likely have a water-rich atmosphere as well. And a water-rich atmosphere would tend to trap heat, which would raise the surface temperature of the planet and then increase the temperature of the hydrosphere. So there's a feedback there that would tend to push these worlds towards warmer climates. And then the other thing that I want to mention as far as coupling between the atmosphere and the surface is that the differences in albedo between, say, a water surface and an ice surface, or even an ice surface versus a snow surface, play a role in setting the temperature balance of the planet. So how much incident radiation are you reflecting back into space changes the expected surface temperature as well. So to really investigate this, you'd need to couple a atmospheric model to the hydrosphere model. And of course, we haven't done that. So we just set the surface temperature, say that that's the surface temperature, for whatever reason, and then investigate the structure of the hydrosphere based on that. And so with that, I want to leave up my summary and conclusions. And I want to thank Baptiste Jeannot and Mike Brown for mentoring me on this work. And then, of course, the UW Astrobiology program for providing the funding that allowed me to work on this for a quarter.
Okay, questions? Yep.
Like interfaces between these layers, like I'm guessing in my head that it doesn't just go water, 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 and then ice sun. So I was just wondering, like, what are those interfaces that look like?
Yeah, so in my model, it does do exactly that. It goes, it goes water, 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 and then ice sun. That's a good question, and I don't have a good kind of mental image about like what it would look like if you were a fish swimming around in that ocean.
Sorry.
Yeah.
Can you go back to like one of your base plots?
And now the arrow keys work. All right.
The Dutch artist, never mind. The temperature on the x-axis, is that at the top or at the bottom of the hydrosphere?
That's it. Yeah, I should have been clear about that. That's at the top of the hydrosphere. So I just labeled that temperature. That's the surface temperature.
Okay, so is there like a way that you could redo that from the bottom of the temperature and then incorporate the kind of whatever heat flow is coming from the mantle into your simulation? Sorry, from the rocky core.
I think so. This would be a better question for Baptiste, who knows much more about this than I do. But as long as you're still, you would still be simulating an adiabatic hydrosphere, but I don't see why you couldn't set another boundary condition for the interior and then solve for the pressure temperature profile between those two boundaries and still have an adiabatic hydrosphere.
And just to be clear, you assume zero heat flow, right?
Yes.
Yeah.
Yeah. Yeah, so the adiabatic approximation, I believe, means that there's no heat flow between layers. There's no heat radiating between layers. So as long as that condition is still met.
Josh.
Thanks for that, Tom. This may be a kind of basic question, but could you provide, as someone who isn't super familiar with high pressure ices, there's some intuition how different they are compared with like ice we have?
Yeah, I don't know how much intuition I can provide there. So I guess what I can say is that, yeah, when we talk about high pressure ices, we're talking about ices that have different crystal structures. For the very high pressure ices, you end up with things happening like the electrons becoming less localized as you compress the water molecules closer together. Eventually, I believe even the hydrogens can become kind of delocalized and float like between oxygen molecules. As far as like intuition about what that looks like I don't know what it would look like if you opened your freezer and had ice 7 in it, except that your freezer would be at the bottom of a planet somewhere, probably.
Baptiste, you want to say something?
I can insert that. Yeah, so I7, for example, you can make cubic crystals out of it instead of hexagonal crystal with Y rotation. Yeah, there's a few examples where you can have can even create square snowflakes. Yeah, with like 4 branches instead of 6. And so the other main property that makes the high pressure ice difference is that they are denser than liquid water. So they would naturally sink at the bottom.
Very cool. Thank you.
Yuck.
Does your model consider the effect of salinity on the its energy? For example, if you add sodium chloride to the system, would it change your model prediction?
Like freezing point depression and that kind of
Yeah,
thing?
it would change the model predictions. This model doesn't incorporate that at all. Obviously, that's a really like natural and I think important extension of this kind of work, because you would expect there to be some solutes there, and that does change. That changes freezing points. That changes the thermodynamic properties. Yeah.
So not yet.
Nick,
So are the density differences between the ICs? In this map back into the mass radius diagram you were showing earlier, like these sorts of, you know, you predict essentially masses and radius of planets with your model that would then inform our knowledge of what we're seeing when we look at exoplanets, if they're not here.
So one kind of problem with doing that is that these hydrospheres do not make up a lot of the radius of the planet. So even for, you know, even going kind of higher on the y-axis than I had, up to 5 or maybe even well, maybe if you get to much larger percentages, they could, but if we're talking about dumping like 1% water by mass on top of something like the Earth, you're not changing the radius enough, I think, that you would really. I'm not confident about what I'm saying, actually, now that I'm saying it out loud. That's a good question. I'm not sure that we're at a point where like doing kind of the inverse problem is like really going to constrain strongly the composition or the amount of water on these planets, because there's too many degeneracies there. It's the amount of iron that you have in the core that controls its density, the amount of water that's also degenerate with how like puffy the atmosphere is or whether there is an atmosphere. So I think there's too many degeneracies there and too much going on to really go from like an observation of the mass and radius of a planet back to how much water is on it. There's people that have kind of tried to do that work in cases where they think you can make arguments for ruling out the presence of an atmosphere, or where you can make arguments for saying that the planet has, you know, a well-constrained composition or a well-constrained density. But in general, I think that's hard to do.
Okay, well, we've reached the top of the hour, so let's thank Haida once again.